Okay, so this is the new topic for your KIN 225 lecture for February 22nd. So this is part 2, and we're going to be covering what's called the bilateral deficit, which is a nervous system or neuromuscular phenomena with strength and with training. And this is the topic of your lab number 4, which you'll be doing in a couple of weeks. So the bilateral deficit, the definition here is that the sum of unilateral strengths is greater than bilateral strength. Another way to describe it is that there's a deficit in force if you do contractions with 2 limbs simultaneously compared to contracting 1 limb at a time. So it seems like you're weaker if you contract 2 limbs at a time as opposed to if you're contracting the same limbs unilaterally or one at a time. And that's why it's called a bilateral deficit. There's a deficit in force if you're contracting 2 legs or 2 limbs at a time. This is best explained by giving an example. So I'm giving the example of a bilateral contraction with the leg press exercise. So you can see the leg press, what that involves. And this is a graph showing your strength abilities. First, when contracting 2 legs at once, as in the picture, so a bilateral contraction, and then contracting the right leg alone and the left leg alone. And the key here is that you notice that the bilateral strength is about 100 kilograms. So you'd expect that the right leg contracting alone and the left leg contracting alone would be about 50 kilograms each, but they're actually 60 kilograms. So it seems like your legs are stronger if they're contracting unilaterally. So if you add these 2 together, you get 120 instead of 100. So the sum of your single leg strengths is greater than your bilateral strength. And that's why it's called the bilateral deficit. It looks like your limbs are weaker if they're contracting at the same time. And this bilateral deficit, a lot of people will have it in the leg press exercise. It's really common in multi-joint exercises. For something like an arm curl, which is a single joint exercise, or knee extension, it's less prevalent. Causes of the bilateral deficit, so there's several theories here. One is that there's when you're contracting bilaterally, there's sensory input from one limb that causes inhibition on the motor neuron innervating the muscle on the opposite limb. Another theory is that there's something going on at the brain center, so there's inhibition of one side of the motor cortex on the other. So when you contract one side of your body, if you're contracting the muscles on the right side of your body, that's controlled by the left side of your brain, and the right side of your brain controls muscles on the left side of your body. And so if you're contracting both sides of your body, right and left limbs at the same time, it's thought that there might be interference between the 2 sides of the brain, and that might cause the bilateral deficit. And then there's a theory that it might be just due to biomechanical factors. So it might be the differences in stabilization that you get when you're doing bilateral versus unilateral contractions. So I'm going to go over each of these and give examples from different experiments. So this first cause is sensory input from one limb causing inhibition on the motor neuron innervating muscles of the opposite limb. And you can see this experimental setup. This setup is to elicit the stretch reflex, so the muscle spindle in the quadriceps. So what happens in this setup is that you have these mallets that automatically come down, these rubber mallets, and they're designed to hit the patellar tendon. So that's the tendon that attaches your quadricep over the knee. So that's hitting the patellar tendon. That causes a rapid stretch in the quadriceps and causes a reflex contraction of the quadriceps. So this leg would kick out when that stretch reflex is elicited. So the rubber mallet comes down, hits the knee, causes a rapid stretch of the quadriceps, activates the muscle spindle. That muscle spindle would send a reflex back to the spinal cord to cause contraction of the quadriceps. You get kicking motion, and you get assess force output with this force transducer. So in this experiment, they elicited the stretch reflex unilaterally, so one leg at a time, and then recorded the force output from the kicking motion, or they elicited the stretch reflex bilaterally with both of these rubber mallets dropping at the same time. And they found that the force output with the bilateral contractions for each leg was lower than the force output with the unilateral contractions. So in other words, there was a bilateral deficit caused by just the eliciting this stretch reflex. So it didn't involve anything from the higher brain centers. It's strictly a reflex down here that goes from your muscle to your spinal cord then back. And so it looked like in the bilateral condition, there's probably some kind of inhibition going on with those reflexes at the muscle level. So this would involve peripheral reflexes and would not involve the higher brain centers. But then again, there's other experiments that show that the bilateral deficit might be due to inhibition at higher brain centers. So inhibition of one side of the motor cortex on the other. So again, the right side of your brain controls the left side of your body. The left side of your brain controls the right side of your body. When activating both sides of the brain at the same time, there might be inhibition between the two. And you can do that by monitoring brain activity when you're doing exercise. So brain activation can be assessed with this type of magnetic resonance imaging called functional magnetic resonance imaging. And you see the experimental setup here. The person is going to be doing contraction with their hands against these wooden mallets. Their brain is going to go into this MRI scanner, and then you can get images of the brain, and the images will tell you what parts of the brain are being activated during the exercise. So this is how it works. The functional magnetic resonance imaging detects changes in, the blank here is hemoglobin oxygenation in the brain. So hemoglobin is a protein that carries oxygen. Sometimes it carries it to your muscles. In this case, it's carrying the oxygen to your brain tissues. And so this imaging technique measures changes in the hemoglobin oxygenation and deoxygenation. So it can tell what parts of the brain are taking up oxygen from the hemoglobin, and then what parts of the brain are not taking up oxygen or becoming deactivated. So it can detect changes in brain activation and brain deactivation by measuring the hemoglobin oxygenation. Essentially, it's measuring oxygen consumption in the brain, and if you're using different parts of your brain, that part of the brain is going to be consuming more oxygen. So using this technique, you can see from this experiment, these are just images from the functional magnetic resonance imaging. And you can see it's a right hand exercise, left hand exercise, and then using both hands. And the activation here was greater if you add up the right and the left side alone versus using both hands at the same time. So if you add up the activation in these two screens when you're doing the unilateral exercise, it's greater than the activation when you're doing bilateral exercise. So in this case, there was a bilateral deficit in brain activation. So showing that the bilateral deficit might be going on at higher brain centers. And the last thing I have for you here is kind of a brain cartoon.